We do have homework for today. I hope you've had a chance to try it out. And we are going to have a quiz on Friday covering the same stuff. Something to look forward to. I want to say a few more words about the subset construction. Actually, what I want to do just real quick at the beginning is a proof that the subset construction works. And this must involve writing things in terms of the formal description, because that's the purpose of the formal description, is so that you can actually prove things about it. Otherwise, you just find yourself gesturing towards the diagrams, which is not a real proof. Remember, the subset construction is that thing that we were doing towards the end last time about how to convert a NFA into a DFA. There's some questions on the homework, by the way, which are about, here's an NFA, you give me a DFA that does the same thing. You can, if you want to, use the subset construction to do that. But actually, the chronology of the book, those questions, they do not intend for you to use the subset construction. You're intended to just look at it, look at the NFA, figure out what is accepted, and then write a DFA which does the same thing. But either way you want to go about it is fine on the homework. Anyway, I want to try to prove that the subset construction works. So how it works, remember we start with the NFA. And I will write it using its formal description. I'll call it N for NFA, I guess. And let's say it has states Q. Just because I'm also going to talk about the DFA that we're going to make. So I'm going to call the states Q. I'm just going to call them Q. I wrote something different on my paper. I'm trying to figure out why. I'm going to call them these. So the NFA in its 5 things. Q is a set of states. That sigma there is the alphabet. A, B, usually, in our examples. Then we have the transition function, which I'm calling delta sub n for the NFA, because we're, in a little bit, going to talk about the transition function for the DFA that we converted into. And then Qn is the starting state for the NFA, and then Fn is the set of accepting states for the NFA. All right? And then we create a DFA out of it, which I will give names to those things too. So the DFA, actually, let's try and sort of fill in the blanks here. The second thing is the DFA has the same alphabet, right? So we don't need to worry too much about that. Although pretty much everything is going to be different. Everything else is going to be different. The set of states of the NFA was Q. Remember, the set of states in the DFA is all possible subsets taken from the NFA states, right? That's why it's called the subset construction. So what I want to write here is the set of all possible subsets of things that come from Q. And you remember how to write that? Yeah?
Is it the P parentheses Q?
Yeah, the power set of Q, right? That is all subsets of things from Q. So what I'm saying there is the states in my DFA correspond to subsets of states from the NFA. That's why that's a power set of Q right there. That's the best I can do for a fancy looking P. All right? What's the transition function? I will just say, I will describe this below. I will comment below. The starting state, actually all of these I'm going to comment below what they are. I'll just call them this for now. And I will say where Q, let's talk about QD, the starting state for the DFA. I hope you remember how you do this, the subset construction. How do you choose what the starting state is? It consists of the original NFA starting state together with anything you can reach by epsilons from there, right? I hope you remember that. I'm going to try and write that here. So QD is, maybe I'll just write, I'll write those words that I just said, but actually there's a cute way to write this using the set theory. It's the original start state actually we have a name for that. It's Qn, right? Together with anything you can reach by epsilons. Also anything reachable by epsilon in the NFA. Actually, we can write this set. So QD is, check it out, see if you agree, delta star n Qn epsilon. I'm using the transition function from the NFA. What does that mean, delta star n Qn epsilon? It means all the states you can get to starting in Qn and doing epsilon, which is exactly what I said in those words there, right? So this is actually a fairly easy to write kind of thing. All right, so that's what the starting state is in the DFA. What is the set of accepting states? Can anyone say in words what that, how do you decide when you have all your subsets, which ones are accepting? Yeah.
Any subset that contains an element that was accepted by the NFA.
Yeah, right. So it's any one of these subsets which contains one of these elements, right? Something from Fn. Those are the ones which are accepted on the NFA. So can I say this is the set of, I'll write it in words first and then we can write something a little fancier. The set of subsets containing some element of Fn. Remember, Fn is the set of things which are accepted on the NFA. This, unfortunately, you can't write in a super compact way. Really, you have to say something like this is all, I will say, S in the power set of Q, such that S intersect Fn is not the empty set. So what that means is it's all of the subsets. That's why I said S in the power set. All of the subsets containing some element of Fn. That means this S, when you intersect it with Fn, there actually is something which is in S and also in Fn. That's the only way really to write this, containing some element of Fn. It means that these sets, when you intersect them, it's not the empty set. There is some element in S and also in Fn. All right. So that's the the set of accepting states, and there is no cuter way to write that. You just have to write like that. And we should say what the transition function on our DFA is. So the transition function, that was kind of the most tricky thing to figure out in my opinion when you're trying to draw those. How you draw the arrows is you consider all possible states in your subset, and then you look for everywhere that those states could possibly go to when you do this or that arrow. So the way to describe this is like so. You think of R as one of your subsets, and I want to say on the DFA, where do you go to if you're in one of these subsets R and you read the letter A? The answer is a subset which consists of all possible places you could end up if you start from some element of R and you do A. So the way to write this is, unfortunately, this also is not, there's not an easy way to write this. So that's a big union there. I'm considering the union of all the possible places. How you read this is everywhere you could possibly end up if you do the letter A on the NFA. And you have to take the union of all those things. All the places you could end up from all of your different states, and you combine all that stuff together. This is pretty abstract set theory nonsense in my opinion. But actually this is kind of the, we're not going to be doing this all day. Give me another 5 minutes and then we'll be done with this stuff. All right? Maybe you don't mind. I don't mind. I could do this all night long. All right, so this is the description of the DFA, all right? It is those 5 things together with, here's the description of what the QD, the FD, and the delta D are. All right? Kind of complicated in my opinion. Anyway, what's our goal here? Our goal is to demonstrate that these 2 machines have the same language. That's the whole point of this, is you start with an NFA, you convert it into a DFA having the same language. So our goal is to show that L of n is equal to L of m, right? That's the whole point of what I want to say in terms of proving that the subset construction is correct. What it means for it to be correct is that the language that you get from the DFA is the same as the language that you get on the NFA. All right? So I want to prove this, and actually, given that we've set everything up nicely, actually the proof will go fairly nicely once we've set it all up properly. So that's our goal. Remember what L of n is? On an NFA, the accepted language, it's the set of all strings, first of all. It's the set of all x in sigma star. Usually it's, A, B star, but this could be any alphabet. Such that, what does it mean? It means when you start in the starting state and you do, so I'm using the delta star from the n. When I start in the starting state, which I called Qn, and you do the string x, I don't know if you remember this. To be accepted in the NFA, it means that this, which is a set here, this contains one of the accepting states. And so, again, the way you have to write that is like this. All right? This is what L of n is. That's just the definition. If you look back, we talked about this a few times ago. I don't really assume that you have this weird formula memorized, but that is what L of n means. This stuff over here, it means the set of all strings, such that when you start in the starting state and you do that string, it has this set of possible destinations, contains some of the accepting states. All right? And what about L of, yeah, question?
So in the delta, I'm just wondering, is the capital R, is that the states in the...
Up here?
Yeah. Is that the states in the DFA? DFA states?
Yeah, so this R represents one of the DFA states, which itself is a set. It's a subset, right? That's why I used a capital R here. It is a subset of states from the original DFA, and that's also why you can say Q is an element of R. Like this R, it is a DFA set, but each of the DFA sets is itself, it is a DFA state, and each of those states is itself a subset of things from the NFA. All right? This is Ln. What is Lm? The language of M. Remember, what is the language of a DFA? That's actually a little bit easier to write down. It's all x in sigma star, such that delta star on the DFA of the starting state of the DFA, which I called QD, and x is in FD, right? That's the definition of the language of a DFA. It's all the strings such that when you do the delta starting from the starting state, the result is an element of the FD. All right. Actually, those two sets, our goal is to show that they are equal, and this we can do fairly easily just by, I'm going to just rewrite the second state, or the second set there. I'm going to rewrite it several times, and hopefully end up, etc. Eventually, I'm going to say equals L of n, so they will be equal. I don't know if I'm going to hit exactly that spot, but that's my goal here. All right. So what am I going to do first? First of all, this is actually the weirdest step of all. The rest of it is just playing around with the notation, rewriting things that are equivalent. But actually, this very first step is the weird step. This is equal to, I'm going to write it down first and then see if we can make sense of it. Oh no, sorry, this is not the weird step yet. I'm going to close the door. All we did here was rewrite what is QD. If you look back in your notes a moment ago, we wrote down what QD is, and it is delta star n of Qn comma epsilon. That's what QD was. So all I did right there was just plugged in for QD. This right here, QD, is equal to that. We just said that before, all right? Coming next is the weird step. That was an easy step. This is the weird step. What can we think about this big thing? Actually, this can simplify. What this says is you start at the starting state of the NFA, you do a bunch of epsilons, and then after that, you follow that by doing the string x. And it turns out, this is a little tricky, and I don't want to get bogged down in the details because I'm already boggy enough here. This is the same as this. Sorry, Qn. I mean an N out there. Yeah, I knew something was wrong here. No. All right. The way you want to think about this, and then in F. Yes. The way you want to think about this is it says I start in Qn and I do epsilon. That is, I do nothing, maybe do some epsilon transitions, but then I follow the string x. That's the same as starting in Qn and just following the string x on the NFA, because the NFA is allowed to do epsilons either before the x or after the x or whatever. All right. This says starting Qn, do epsilon, and then from there do x. That's the same as this, starting Qn and do x. And implicit in the NFA is you can do epsilon whatever you want. All right. Continue rewriting. Okay. So the rest are more straightforward steps. To say this is in FD, remember the definition of FD? It is all sets. Here's FD. All sets where their intersection with Fn is not empty. So to say this is in FD, it means the intersection of this and Fn is not empty. I'm going to write that. Delta star n q n x intersect Fn, not empty. All right? Because that's what it means to be in FD. FD is the set of all things for which intersect with Fn is not empty. So, all right, are we there yet? Yes, actually that is L of n. You can see it's the same up top. So this may be the most elaborate set theory proof that we talk about all semester. So if you're feeling like you should have dropped this class because of this, don't drop this class because of this. Drop the class for other reasons maybe, but this is not, we're not going to do this every day. But yeah, this is another example of if you set up all the set theory correctly, then the proof becomes just a matter of plugging things in correctly and rewriting all the sets. The set theory actually works very nicely to do this proof, even though, I mean, if you're not accustomed to it, you might not feel like this is a really nice proof, but everything is very precisely set up so that it all just kind of cranks through by rewriting stuff. All right. Are there any questions about that? I'm going to get on to something different as soon as possible. All right, great. So I hope you believe now, I don't know if you believe more or less now that L of m is really equal. The language of the DFA that you get after that really is the same as the language of the NFA that you started with. All right. Excellent. Actually, this is pretty much the last that I want to talk about NFAs for a while. And DFAs, actually, we're going to move on to something completely different, another type of machine today. But as sort of a summary of where we've been so far, we talked about DFAs, and their languages are called the regular languages. And then we talked about NFAs, but it turns out actually their languages are also the regular languages. So I would like to just sort of summarize. DFA and NFA have the same computational power. All right? What they can compute is the regular languages, and that's it. So actually, when people talk about these things often, when computer scientists are talking about these, or mathematicians, they will often just refer to them as finite machines or finite state machines. And nobody asks, wait, would you mean DFA or NFA? The answer is usually, well, it doesn't really matter. I mean, if you want to actually draw the diagram, then it matters. But in terms of what kinds of sets they can compute, it doesn't matter. DFA and NFA, they can compute the same sets. They are the finite state machines. All right? So they have the same computational power, and that is they both can compute regular languages, right? And what we know about regular languages, we also just in the vein of summarizing what we've done so far, we also talked quite a bit recently about closure properties for regular languages. If this language is regular, then this other language is regular. So I will just summarize that also. I'll write this like a theorem. We've already talked about the proof though. Regular languages are closed under complements was the first thing. And all of these things, on our first test or something, I might ask you to do an example. This one is very easy. If I show you a DFA, show me a DFA to accept the complement. For that, you just flip all the accepting to rejecting states and rejecting to accepting. This only works on a DFA. Actually, NFA, if you flip-flop the states, you don't get the complement because on an NFA, some strings are rejected because they actually end in a rejecting state, but some strings are rejected because they get stuck in the diagram. And when you flip-flop the states, you don't actually get the complement. But anyway, complements. Also unions, also intersections. For both of these, you use the product construction. Also, set difference. This is actually on the homework for tonight. Right? I don't remember what number it was, but if you have two regular language, L1 and L2, can you make a DFA for L1 minus L2? And the answer is yes, you can. And it also uses the product construction. You just have to say which are the accepting states. And also the concatenation of languages. How do you get the concatenation of two regular languages? You can do that. This is actually hard to do with the DFA, but with the NFA it's easy. You do this kind of thing, right? That was the setup for combining two NFAs together and get concatenation. I said that's because you're using epsilons, you can only really do this for NFAs. Can you do concatenate two DFAs? The answer is, like, in theory, yes, you must be able to, because the concatenation of two NFAs, you could then convert that into a DFA. You would never really want to do that, but the regular languages are closed under concatenation. All right? Excellent. Does that summarize everything we've ever said so far? Maybe. It's close. This is pretty much all we've been talking about all along. All right. Let's talk about a new type of machine. Unless there are any questions about this stuff, I think we're all set on that. All right. A new type of machine. Actually, what we're about to talk about is very different. It's not just a slight variation on these. And it doesn't even look like a machine at all, but you will agree that it behaves in a very similar kind of framework. These are called regular expressions. And this is something you may have encountered in programming before, or in other computer science classes. Regular expressions are actually very down to earth, and people use them all the time in the real world. People don't actually program using DFAs and NFAs in the real world, but regular expressions are used all the time to do very fancy things. I want to talk about regular expressions and try to fit it into these frameworks. We don't usually think of a regular expression as a machine by itself, but these are a regular expression, which I'm usually going to write people write it like that. Regex, I don't know. I say regex, even though it's not regular, it's regular, but whatever. A regular expression is a systematic way of accepting or rejecting strings. And so from that point of view, it fits in very nicely with our DFA, NFA types machines. Although when you write it down, it doesn't look like a machine at all. So a regular expression is a systematic way of accepting or rejecting strings. All right. And I'll just give you an example what they look like. So, just like our DFAs, NFAs, we specify an alphabet to begin with. So on the alphabet A, B, a regular expression looks like something like, this is just an example. It's not a diagram at all, really. It's a bunch of parentheses. It has some stars, some pluses, like that. This is what a regular expression looks like on a particular alphabet. Now, I'll say if you are familiar with regular expressions, sort of in real life coding languages, the notation is sometimes different. The star is used when you see a star in a regular expression, say in a real programming language. It means what I mean by star. The plus is used differently. When we write a plus, usually in a programming language, regular expressions use the pipe there, the vertical bar. But anyway, this is what a regular expression looks like. And because I know something about regular expressions, I can just sort of look at that and tell you what strings this will accept and what strings it will reject. So that's what we're going to talk about. By the end of today, maybe we will have talked about all the little pieces we have to talk about. I mean, you can tell there are certain, it basically uses the letters in the alphabet, the A and the B, together with certain operations. So we just need to understand, what do the parentheses mean? What does the star mean? What does the plus mean? And once you understand all that, you pretty much understand everything. This defines a language. For instance, if I call this R, call the whole regular expression, then this makes a language, which we're going to write like L of R, right? And in this case, just because I know something, I know, for example, here, ABA is accepted. Now when you talk about regular expressions, we don't typically use the word accepted, but ABA is in the language generated by this regular expression. And something like BB is not in this language. So eventually, we will learn to read that weird-looking thing there and tell what is accepted and what is not. All right, so here's very basics of how it works. We basically just need to talk about what do those little operations mean. So how it works. Given an alphabet, given some alphabet, sigma, a regular expression consists of consistis, I wrote, of what can be in there? Letters, first of all, from the alphabet. It could also have plus, which is an operation. It can also have the star, which you saw in that one. It can also have parentheses. It can also, this is not always useful, but it can also have the empty string. That can appear in the regular expression sometimes. It didn't in that example that I did before. And also, this one is essentially never used, but it is legal to put a special character which represents the empty set in the regular expression. All right? So I have to tell you what each little piece of a regular expression represents. If you see a letter in there, like you did up here, those letters actually just represent themselves. So like this A here means a A. This B means a B. So the letters represent themselves. Come on. Letters represent themselves. So, for example, if my regular expression is just A, then what is the language generated by that? It's just A. So this regular expression, A, matches, we say, so we don't say accept or reject when we're talking about regular expressions. We say it matches, this regular expression, it matches the string A and no other strings. Only A. All right, the empty set, if you see that, this gives the empty language, which actually you never use this in real world programming with regular expressions, which is why, even if you've seen them before, you probably haven't seen this. It's essentially never useful when you're trying to use regular expressions in programming, but for theoretical reasons, you need to have this. This gives the empty set, so L of empty set is defined to be, well, the empty set. It matches no strings, right? No strings are accepted, if you want to think of it in that way. And the empty string, this one matches the empty string. So that the empty string also just sort of represents itself. So if you say, what's the language of the empty string as a regular expression? It's that. It matches just the empty string and nothing else. All right. These, what I've said so far, these three things are referred to as atomic regular expressions. So letters, the empty set, and the sigma are the three, these are called atomic regular expressions. And every other regular expression is created by using the operations, the plus, the star, and the parentheses. All right? But these are the very basic building blocks are the individual letters and the empty string and also the empty set, which, like I said, we almost never use the empty set, but you have to include it for theoretical reasons. All right? Those are the atomic regular expressions. They're only really interesting when you start combining them with the operations. So there are three operations by which you can combine atomics together and make more interesting, more complicated regular expressions. So the first is plus, which you saw in there. I will say in programming, usually the plus in a regular expression means something else. In programming, it's the vertical bar, that's the pipe, you know, the shift backslash on your keyboard. This means or. All right, the plus operation, it means or. So, for example, what is the language generated by A plus B? Well, the A by itself matches only A. The B by itself matches only B. And A plus B means it matches A or B. So this language would be just that, A or B. Right? When I say match is like in regular expressions what the word that is used instead of accepting or rejecting. Yeah?
And that's not like it contains, that's the whole string is like a variable.
Yes, that's right. Yeah, so, yes. Usually when regular expressions are used in a programming language, you are matching substrings of a larger string, but we're not going to talk about it in that sense. Yeah. You are just matching the entire string, which for A plus B, it just has to be A or it has to be B. Okay? In general, if you have two regular expressions and you combine them with a plus, so imagine R1 and R2 maybe they are themselves more complicated regular expressions. The language generated is this. It's the language of R1 union the language of R2. That's the or, right? This actually is the official definition of what the plus means. Whenever you see the plus, it makes the union of those two regular expressions. That's the definition of the plus as an operation. All right? I said general. I meant to write in general, comma. All right? That's what the plus means. It means the union. Okay? What about the star? The star. This is our next operation. The star here actually is meant to have the same meaning as the star in set theory that we've been using so far, like, you know, the sigma star. When I write sigma star, that means all possible strings you can get using things from sigma. So what the star does is it matches the preceding thing, I will say 0 or more times. You think of the star as representing repetition, although that it's not exactly repetition. I'll try to say what I mean by that in a moment. But I will say, like, as a sidebar, this is like when you say AB star, what that means is it's the set of all things that you get by doing A's and B's over and over again in whatever order you want. You could say informally, it means you are repeating A's and B's, but it doesn't actually mean repeating A like A. It means you can mix them all together however you like. But anyway, so the way I'm going to describe this is the star means you can do this stuff as much as you want, 0 or more times. All right, so the star matches the preceding thing 0 or more times. So for example, what if I just do A star? What's the language generated by A star? It means you do A's over and over again, 0 or more times. This, you know, is what we would typically write like this, A to the n, and in the natural numbers, right? That's how the star works. Or something like, now you can use parentheses. The parentheses mean like parentheses in ordinary math. It just is a way of grouping things. So if I say A plus B star, can anybody say in words, what does that represent?
I do have a question.
Or a question? Yeah, go ahead.
For do parentheses, is that a precedence too, or is it just like you're still reading it left to right, but you do this together? Like, is it precedence, like word operations type thing, or no?
Yes. Yeah, so, well, yes. It means you do the stuff inside the parentheses first, and then you do what's outside.
Okay.
And in this usage, A plus B star, it also means the star applies to everything inside the parentheses. Yeah. Can anybody say just in words what that represents?
It's like A as many times or B as many times.
Okay, it's actually not quite. This means, so what's inside the parentheses is just A or B. The interpretation of the star is you can do that thing as many times as you like, where that thing is an A or a B, and you can do it again and again and again. It's a little bit different. So this matches any string made of A's and B's. So it doesn't have to be, it could be that, but it also could be like this. When you're doing the star, you are repeating things, but you don't have to do the same thing every time. All right? That's the meaning of the star. Or it could be BB. Could even be the empty string, etc. Right? Just anything that matches with A's and B's. Yeah.
And the whole string has to only have A's and B's.
That's right. Yeah. This would not, I mean, it would not match something like A, B, C, right? Because C cannot be made by some repetition of A's and B's. Yeah. This is different, and this is what I think, if you wanted to say what she said before, my interpretation of what she said before at least, is actually this. A star plus B star, that's different. That means you can repeat A's or repeat B's. But this does not allow for mixing some A's and then some B's, right? So this actually matches any A to the n or any B to the n, which is quite different from the A plus B star. All right? I don't know if anybody was going to ask me, can you distribute the star across addition? The answer is no, because those are different, right? A plus B, the whole thing star, is not the same as A star plus B star. Yeah.
So, I guess why does having the star around the parentheses mean you could do any number of both in the same string?
Yeah, the star means,
But having it like on the individual letters means it can either be one or the other, but you can't.
right.
do both.
Yeah, the star means you can repeat or do many times whatever precedes it. And in this case, what precedes it is either A or B. So the thing you're repeating can be either a A or a B every time. Whereas down here, it has to be either an A every time or a B every time.
So it's kind of like you're taking the string and you're repeatedly checking for A or B, which is why.
Yeah, right. Yeah, every little piece of this has to match A plus B. Whereas here, every piece of this, either every piece has to match a A or every piece has to match a B. Yeah. All right. This is the star in regular expressions. It means the same thing as the star in set theory. So generally, L of R star, this is the true definition, although we don't typically think of it this way, but it is actually L of R, the whole thing, star. The star in set theory means the same thing. It means you take elements from that set and you do those over and over again, but you don't have to choose the same one every time. You can choose different elements every time, but you do 0 or more repetitions of elements from that set. All right. I said there were 3 operations, although these are all the ones that you've seen in that example that I did at the beginning. The plus, the star, one more operation. Actually, I did use it. You probably just didn't think about it. Concatenation. That is when you just write 2 things right next to each other. There's no symbol for this operation. It's just putting 2 things next to each other. And it means, exactly what you would think it means. So if I write AB, nobody said, whoa, what does that mean? Can you really put an A next to a B? Yes, it means AB. It means A followed by B. So concatenation, it means exactly what you think it means. This matches just that string AB, right? Once you include concatenation, things can get a lot more interesting. So for instance, the language of AAB, this is not terribly interesting, plus BA, that would match only these 2 strings, right? AAB, and it also matches BA. All right, not terribly interesting. But you can do things like, what is the language of A star B? This means you can do as many A's as you want, followed by a B. How would I write that in more ordinary set theory? You want to say? Yeah?
Would be A to the N and B.
A to the N, B, yeah, where N is any natural number. Right, A star B is A to the N, B. Great, how about something like L of B star, A star? This means you can do a bunch of B's followed by a bunch of A's, where the bunch of could be 0, right? Can anyone say, how would I write that as a set?
B to the N, A to the N.
Mm-hmm. I like your attention to detail on the exponents. The N and the M. Don't use the same exponent both times, because I'm not saying that there's the same number of B's and A's. It's just any number of B's followed by any number of A's. Great. How about, just to be cute about it, AB star. This means repetitions of AB. So you could do AB, or AB, or AB. This would be written something like AB to the N. Right? That's repetitions of AB. All right, and we can mix and match all of these operations. How about, I'm going to say even some more fancy ones. How about L of A plus B squared star? Now this one is not very convenient to write using the set notation like I did those other ones, but can anyone describe in words what this would be? say some words like it's all strings that are made of something, something, something. Yeah?
So is it all strings made of like A's or groups of 2 B's?
Yeah, right. So it's any string with a mixture of A's and B's, but every B's got to be a group of 2 B's. So maybe I'll just say all strings made of a mixture of A's and BB's, right? Of course, B squared, that square is not a special regular expression thing. I just mean BB when I write B squared. All right? Great. I meant to say the concatenation operation. Oh, actually, can we just revisit the original thing that I wrote up at the very beginning and see if we can make sense of it now? It's kind of complicated. I'm going to copy this. Here was that thing I said at the beginning. What kind of things does this match? Now, this is not easy to write down sort of in words even what is matched by this string, but how I would write this is, first of all, everything that this matches must end with an A, because it's got some stuff here followed by an A, all right? So, in order to be matched here, it must end with an A. What else must it have? It either is a bunch of A, B's, followed by A, or it's a bunch of B's followed by A, B, A. So that's what is matched here. So this, I'll try to write that in words, although it matches any string like, taking the first option from the plus, that could be a string that looks like AB to the n followed by A. Or taking the second option from the plus, it looks like B to the n, A, B, A. All right? And that's what that regular expression matches. Yeah?
And you could have a string made up of both of those pieces, right?
No. It has to be one or the other, I think. For instance, it could not be, say, this followed immediately by this other one. Because if you wanted that, you would put a star around everything. Then you could repeat and mix and match the two parts.
Like repeating that rule itself.
Yeah, but without that star on the outside, you're only allowed to do sort of this plus can only have 2 outputs. And that's it. You can't revisit them. All right? The regular expressions are a great way, actually, of, I could imagine a universe in which, like all of mathematics, rather than being based on set theory notation written in this way, actually, it might seem easier to write sets always like this, right? I mean, they look nicer sometimes, and certainly in these 2 examples, the regular expression is very easy to write, whereas the description in terms of as a set is much more complicated. Why don't we all just learn as, mathematical kids in discrete math? Why don't we learn to write everything as regular expressions? Because it seems like more powerful. I will say, it's still a question at this point. We should, when we're going to try to ask questions about regular expressions similar to ones we've asked already, and that is, what are the possible languages you can actually generate using these operations? Maybe the operations actually don't really get you all that much, or maybe they do. That's what we're going to talk about in the future. I'm going to do some real life regular expressions too next time, just to show you how they work in the real world. See you then.